Plutonium-239 is an isotope of plutonium. Plutonium-239 is the primary fissile isotope used for the production of nuclear weapons, although uranium-235 has also been used. Plutonium-239 is also one of the three main isotopes demonstrated usable as fuel in thermal spectrum nuclear reactors, along with uranium-235 and uranium-233. Plutonium-239 has a half-life of 24,110 years. Nuclear properties: the nuclear properties of plutonium-239, as well as the ability to produce large amounts of nearly pure Pu-239 more cheaply than highly enriched weapons-grade uranium-235, led to its use in nuclear weapons and nuclear power stations. The fissioning of an atom of uranium-235 in the reactor of a nuclear power plant produces 2 to 3 neutrons, and these neutrons can be absorbed by uranium-238 to produce plutonium-239 and other isotopes. Plutonium-239 can also absorb neutrons and fission along with the uranium-235 in a reactor. Of all the common nuclear fuels, Pu-239 has the smallest critical mass. A spherical and tamped critical mass is about 11 kilograms, 10.2 centimeters in diameter. Using appropriate triggers, neutron reflectors, implosion geometry and tampers, this critical mass can be reduced by more than twofold. This optimization usually requires a large nuclear development organization supported by a sovereign nation. The fission of one atom of Pu-239 generates 207.1 MeV equals 3.318 A, 1011 J, that is 19.98 TJ mol equals 83.61 TJ kg. Manufacturing: plutonium is made from U-238. Pu-239 is normally created in nuclear reactors by transmutation of individual atoms of one of the isotopes of uranium present in the fuel rods. Occasionally, when an atom of U-238 is exposed to neutron radiation, its nucleus will capture a neutron, changing it to U-239. This happens more easily with lower kinetic energy. The U-239 then rapidly undergoes 2 beta decays, becoming Pu-239. After the 238U absorbs a neutron to become 239U, it then emits an electron and an antineutrino by I-squared a decay to become Neptunium-239 and then emits another electron and antineutrino by a second I-squared a decay to become 239Pu. Fission activity is relatively rare, so even after significant exposure, the Pu-239 is still mixed with a great deal of U-238, oxygen, other components of the original material, and fission products. Only if the fuel has been exposed for a few days in the reactor, can the Pu-239 be chemically separated from the rest of the material to yield high-purity Pu-239 metal. Pu-239 has a higher probability for fission than U-235 and a larger number of neutrons produced per fission event, so it has a smaller critical mass. Pure Pu-239 also has a reasonably low rate of neutron emission due to spontaneous fission, making it feasible to assemble a mass that is highly supercritical before a detonation chain reaction begins. In practice, however, reactor-bred plutonium will invariably contain a certain amount of Pu-240 due to the tendency of Pu-239 to absorb an additional neutron during production. Pu-240 has a high rate of spontaneous fission events, making it an undesirable contaminant. As a result, plutonium containing a significant fraction of Pu-240 is not well suited to use in nuclear weapons. It emits neutron radiation, making handling more difficult, and its presence can lead to a fissile in which a small explosion occurs, destroying the weapon but not causing fission of a significant fraction of the fuel. It is because of this limitation that plutonium-based weapons must be implosion type, rather than gun type. Moreover, Pu-239 and Pu-240 cannot be chemically distinguished, so expensive and difficult isotope separation would be necessary to separate them. Weapons-grade plutonium is defined as containing no more than 7% Pu-240. This is achieved by only exposing U-238 to neutron sources for short periods of time to minimize the Pu-240 produced. Pu-240 exposed to alpha particles will incite a nuclear fission. Plutonium is classified according to the percentage of the contaminant plutonium-240 that it contains, supergrade to a 3%, weapons grade less than 7%, fuel grade 7 euro 18%, reactor grade 18% or more. A nuclear reactor that is used to produce plutonium for weapons therefore generally has a means for exposing U-238 to neutron radiation and for frequently replacing the irradiated U-238 with new U-238. A reactor running on unenriched or moderately enriched uranium contains a great deal of U-238. However, most commercial nuclear power reactor designs require the entire reactor to shut down, often for weeks, in order to change the fuel elements. They therefore produce plutonium in a mix of isotopes that is not well suited to weapon construction. Such a reactor could have machinery added that would permit U-238 slugs to be placed near the core and changed frequently, or it could be shut down frequently, so proliferation is a concern. For this reason, the International Atomic Energy Agency inspects licensed reactors often. A few commercial power reactor designs, such as the Reactor Bolshoi Moshchnesty Kanonye and pressurized heavy water reactor, do permit refueling without shutdowns, and they may pose a proliferation risk. By contrast, the Canadian CANDU heavy water moderated natural uranium-fueled reactor can also be refueled while operating, but it normally consumes most of the Pu-239 it produces in situ. Thus, it is not only inherently less proliferative than most reactors, but can even be operated as an actinide incinerator. The American IFR can also be operated in an incineration mode, having some advantages in not building up the Pu-242 isotope or the long-lived actinides, either of which cannot be easily burned except in a fast reactor. Also, AFR fuel has a high proportion of burnable isotopes, while in CANDU an inert material is needed to dilute the fuel. This means the IFR can burn a higher fraction of its fuel before needing reprocessing. Most plutonium is produced in research reactors or plutonium production reactors called breeder reactors because they produce more plutonium than they consume fuel. In principle, such reactors make extremely efficient use of natural uranium. In practice, their construction and operation is sufficiently difficult that they are generally only used to produce plutonium. Breeder reactors are generally fast reactors, since fast neutrons are somewhat more efficient at plutonium production. Plutonium-239 is more frequently used in nuclear weapons than uranium-235, as it is easier to obtain in a quantity of critical mass. Both plutonium-239 and uranium-235 are obtained from natural uranium, which primarily consists of uranium-238 but contains traces of other isotopes such as 235. The process of enriching uranium, i.e. increasing the ratio of U-235 to U-238 to weapons grade, is generally a more lengthy and costly process than the production of plutonium-239 from U-238 and subsequent reprocessing. Supergrade plutonium the supergrade fission fuel, which has less radioactivity, is used in the primary stage of U.S. Navy nuclear weapons in place of the conventional plutonium used in the Air Force's versions. Supergrade is industry parlance for plutonium alloy bearing an exceptionally high fraction of Pu-239, leaving a very low amount of Pu-240, which is a high spontaneous fission isotope. Such plutonium is produced from fuel rods that have been irradiated a very short time as measured in MW day-ton burn-up. Such low irradiation times limit the amount of additional neutron capture and therefore buildup of alternate isotope products such as Pu-240 in the rod, and also by consequence is considerably more expensive to produce, needing far more rods irradiated and processed for a given amount of plutonium. Plutonium-240, in addition to being a neutron emitter after fission, is a gamma emitter in that process as well, and so is responsible for a large fraction of the radiation from stored nuclear weapons. Submarine crew members routinely operate in close proximity to stored weapons in torpedo rooms, unlike Air Force missiles where exposures are relatively brief, hence justifying the additional costs of the premium supergrade alloy used on many naval nuclear torpedo weapons. Supergrade plutonium is used in W-80 warheads. In nuclear power reactors, in any operating nuclear reactor containing U-238, some plutonium-239 will accumulate in the nuclear fuel. Unlike reactors used to produce weapons-grade plutonium, commercial nuclear power reactors typically operate at a high burnup that allows a significant amount of plutonium to build up in irradiated reactor fuel. Plutonium-239 will be present both in the reactor core during operation and in spent nuclear fuel that has been removed from the reactor at the end of the fuel assembly, a unregistered trademark S service life. Spent nuclear fuel commonly contains about 0.8% plutonium-239. Plutonium-239 present in reactor fuel can absorb neutrons and fission just as uranium-235 can. Since plutonium-239 is constantly being created in the reactor core during operation, the use of plutonium-239 as nuclear fuel in power plants can occur without reprocessing of spent fuel. The plutonium-239 is fissioned in the same fuel rods in which it is produced. Fissioning of plutonium-239 provides about one-third of the total energy produced in a typical commercial nuclear power plant. Reactor fuel would accumulate much more than 0.8% plutonium-239 during its service life if some plutonium-239 were not constantly being burned off by fissioning. A small percentage of plutonium-239 can be deliberately added to fresh nuclear fuel. Such fuel is called MOX fuel, as it contains a mixture of uranium oxide and plutonium oxide. The addition of plutonium-239 reduces or eliminates the need to enrich the uranium in the fuel. Hazards: plutonium-239 emits alpha particles to become the fairly harmless uranium-235. As an alpha emitter, plutonium-239 is not particularly dangerous as an external radiation source, but if it is ingested or breathed in as dust it is very dangerous and carcinogenic. It has been estimated that a pound of plutonium inhaled as plutonium oxide dust could give cancer to 2 million people. Therefore as little as a milligram would be quite likely to cause cancer in a person. As a heavy metal, plutonium is also toxic. See also plutonium precautions. Weapons-grade plutonium can be used to make nuclear weapons, and there is danger of it falling into the wrong hands. Its storage must be very secure. See also, Teller-Ulam design. References: Physical, Nuclear, and Chemical Properties of Plutonium. Institute for Energy and Environmental Research. Retrieved November 20, 2015. FAS Nuclear Weapons Design FAQ, Access September 2, 2010, AB Table of Physical and Chemical Constants, Sec 4.7.1, Nuclear Fission. K and Labie Online. Jeremy J. Whitlock. The Evolution of CANDU Fuel Cycles and Their Potential Contribution to World Peace. Haller, Jerry. James D. Navratil. Radioactivity, Ionizing Radiation, and Nuclear Energy. No, Converge. Pages 102. ISBN 80-7302-053-X. Bernard L. Cohen. Chapter 13. Plutonium and Bombs. The Nuclear Energy Option. Plenum Press. ISBN 978-0306435676. Archived from the original on July 21, 2013. External links: NLM Hazardous Substances Data Bank, Plutonium, Radioactive, Table of Nuclides with Pu-239 data at K and Labie Online, Half-life of Plutonium-239.